So this is going to be the second half for section 8.4. This is kind of a long section. That's because it has to go through the details of defining vectors in a particular geometrical space. So in this case, it's the coordinate plane, which is a Euclidean space, a two-dimensional plane that we can do Euclidean geometry on. So it's a very special plane that we use all throughout our academic career as secondary students. So where do we leave off? We were here, and they make a small little discussion of this, and then they make a bunch of homework problems on the exercises for this particular section, but they only discuss this in very little detail. So what I'm going to do is I'm going to go ahead and add on to that over here somewhere. So the basic idea, first off, we just defined the idea of adding vectors in the coordinate plane. The question becomes, is there a way that we can become independent of the coordinate system? And instead of talking about a vector with respect to a coordinate grid and coordinates themselves, can I get rid of the coordinates altogether and just talk about vectors being generated by maybe, let's say, a small set of vectors that if I add them, I can form any vector I want? The question is, or the answer to that question is yeah. So especially on a two-dimensional plane, the smallest number of vectors you need to do it is 2. And these 2 vectors, we can choose them. They just can't be scalar multiples of each other. They have to have some difference in a directional angle, and in a sense, that's going to be the requirement. But can I just can I come up with 2 vectors from which we can define all vectors by addition and scalar multiplication? And the answer is yes. So if I'd like to, we can express any vector in terms of these other 2 vectors. Now, it turns out that there is a most intuitive case, and these 2 vectors are going to run along the horizontal direction and the vertical direction, respectively. So what we do is we take what are called unit vectors. A unit vector, which they defined over there, a unit vector, it's in the name. This is a vector. We'll call this U, with a magnitude equal to 1. So a unit vector is a vector with magnitude unit 1. We can give a distinction between vectors and unit vectors using not an arrow on top, but maybe like a little hat on top. So a vector that has length 1 will have a little hat on top. This is normally how we do that. So there are 2 fundamental unit vectors from which we can write all vectors in the two-dimensional space. One of them is the unit vector in the x direction. So I'll draw a vector this way in that direction. This is the x axis, this is the y axis. We're going to call that vector I hat. So it's an I but with a hat on top. So instead of the dot that we normally use for I, we'll use a hat. And the hat's there to signify that it's a unit vector. Now, that unit vector, if we want to write it in terms of x and y components, it is a 1 x component and a 0 y component. That's the definition for the I vector. Then we take the other vector to be the same distance, but with a 90-degree angle from there. So the I vector is a 0-degree angle. The j vector in this case, which is the vertical, is the 90-degree angle. And this is 0, 1. So that way it has a distance of 1 away from the origin, or a length or a magnitude of 1. So those are my 2 vectors. These 2 vectors in mathematics, or in what we call linear algebra or vector algebra, these 2 form a basis. And this is like not a trivial basis, but like a very intuitive one. There's a name for it, and I keep forgetting what it is. It's like a fundamental basis. This is the most intuitive one. So we have 2 vectors, I and j, and from these 2 vectors, we can generate any vector. So let's say I have this vector out over here called u. So from here to here, this is u. We can rewrite u in terms of I and j. And the way that we do that is we scale I and j to the exact distances or the exact magnitudes that the horizontal and vector components are. So if this distance out here is a, and if this distance out this way, actually, and I'll call this one a, this one b. A is horizontal, B is vertical. So whatever A is, in this case I drew it in the third quadrant, so both A and B have negative values to them. Then what we do is we take A as a multiplier on I and B as a multiplier on J. So U would end up equaling to A times I plus B times J. And that is exactly the same thing as writing the vector A comma B. So you can write it as a vector in the ordered pair way, so that way you just write the components A and B, or you can write it as the expansion or the linear combination of I and J, and that would be AI plus BJ in that order. So that's the whole idea here. So you can write any vector like that. That's given here. So this is a unit vector and then we have our two basis vectors I and J. And because they are, what's it called? They're able to write this in boldface, they just write them in bold. They don't write them with hats. But normally in a textbook, especially like a physics textbook, to signify a unit vector, they draw a little hat on top, if you're drawing this by hand. And that's literally it. So we'll move on to example 5 in a little bit, before or after we define what we call the dot product. And after we define the dot product, how many things are we going to go over? There's still quite a bit, so it's going to be like another full video. So there's only two more examples, but there's quite a bit of stuff that we got to know between. So a dot product. So a dot product is a way that we multiply two vectors. And there's a physical meaning behind them, or an intuitive meaning behind them. And we don't get to it too much, except for understanding it in terms of the angle between the vectors. So really, the purpose that this is going to serve is that this is going to, or at least in this class, it's going to give us the mechanism for finding the angle between two vectors without having to draw the vectors themselves and solve a trigonometric problem. We can just turn it into a quick vector problem, and we can solve for the angles in between. So a dot product. So we're going to define the dot product between two vectors to be a scalar quantity this way. So if U has components A and B, and V has X and Y components C and D, then we take what we call the dot product, also known as the scalar product. So the reason why it has that name, scalar product, it's because the end result is not a vector. So we would like to multiply two vectors and get a vector as a result. This one will take two vectors as an input, and it's going to spit out just a real number, not a vector. So we call it the scalar product because the end result is a scalar. Another common name in higher order mathematics is an inner product. Not exactly the same as a dot product, but it boils down to this dot product in two dimensions on the real coordinate plane. So an inner product in two real dimensions ends up becoming the scalar product. Inner products are abstractions of these dot products in different algebraic spaces. So the scalar product then, which they use the scalar product a lot in physics. A lot of the what's it called, theories, physical theories. One notable one would be Maxwell's equations. So Maxwell's theory of the electromagnetic field, macroscopically that is, because then there's also nanoscopically where we're talking about quantum mechanics. At the macroscopic level, Maxwell still reigns supreme, and he has four equations that describe, and there's a little fifth one, which is like a continuity equation or a conservation equation. It's four big vector equations, and they're calculus equations, and two of them are written in terms of a dot product. The other two are written in terms of a different product known as the vector product, not the scalar product. But in order to have a vector product, we need a third dimension. So either way, so dot products are still used a lot in physics. They have a physical meaning behind them if we take them to represent scalar or actual quantities, physical quantities. So anyway, the definition: if A, B, and C, D are the X and Y components for U and V respectively, then we take the dot product definition this way. You multiply the horizontal parts, you multiply the vertical parts together, and then you add those two products. So it's AC plus BD. So it's the sum of the products of the components, the corresponding components. Okay, so it's the sum of the product, if I fill this in, the product of their first components and the product of their second components. So you take the product of the first components, product of the second components, and then add those two products together. And you get the scalar product as a result. So number 5, find each dot product. So -5, 2, and that's going to be dotted with, and that's normally how we describe it. That's a very common way. So u dot v. So I'm going to dot these two vectors as if it were a verb. So we multiply those two together, and according to the definition, it's -5 times -2, and then plus. You add that product with the other product. 2 times -4. Then we just simplify it. -5 times -2 is 10. That's going to end up being a -8, and we get a 2. So for letter A, it's simply 2. Letter B, 10, -1, 1, 10. And by definition, you take the x components and multiply them, 10 times 1. You add it with the product of the y components, -1 times 10. You get 10 minus 10, and that equals to 0. Now, this was a very interesting example when we end up getting 0. And there's a numerical pattern that this fits in order for us to get 0. So it's not the only way to get it, but it's definitely a way to get it. Notice how the x and the y's are switched. So that way one of those pairs has a negative product, and they cancel out to 0. So you end up getting the same magnitude for both, and then they cancel each other out in the end. So since vectors are directional quantities and they're straight linear objects, this is the same thing as taking a line with a slope of -1/10, and then we're taking a dot product with it, another vector that has a slope of 10/1. So if I draw both of those lines, the first line has a slope of -1/10. And why did I get that slope? It's rise over run, y over x, so it's the y component divided by the x component. -1/10 is the first one. Then the other one, same thing, rise over run, 10/1. So if you remember, those two numbers switched. So this was -1/10. This is positive 10/1. Those are negative reciprocals of each other. If you remember in geometry, two lines that have the slopes that compare this way, that they're negative reciprocals of each other, how do those two lines compare to each other geometrically? They're perpendicular to each other. So the dot product is actually built this way on purpose to be 0 if the vectors are perpendicular to each other. That's the actual geometrical interpretation of a dot product. If you take the dot product between two vectors that are perpendicular to each other, you should get 0. It's going to end up being that way. So there's an elaboration on that idea, and we're going to give a, We're going to give an exact representation of the dot product in terms of an angle. There's a way to do it, and I'm kind of debating right now as to whether or not I should include that as part of the lesson. It's a very, very long proof. So we'll see. If anything, I'll start it, and then if I don't like it, I'll just edit it out. So, properties of the dot product. And these aren't things that we should just be taking at face value. All of these properties should be proven. Right, so I might want to prove a few of these. For all vectors u, v, and w, and real numbers k, the following hold. U dot v is equal to v dot u. What does that mean? The order in which I take the dot product of two vectors does not matter. And that's not one that's obvious. The order in which I take the dot product doesn't matter. So let's say u dot v, and let's say u is ab, and we're taking the dot product of that with v, and let's say that's cd. And the definition of that is ac plus bd. Now if I had switched the order, you would end up getting, well, v dot u is equal to ca plus db. But because we're multiplying two numbers, a and c, c and a, we'll have the same product. D and b, b and d, doesn't matter what order I multiply those two, I get the same answer. So yeah, it is the same thing as if I had just reversed the order. So dot product is commutative. That's the first property. Second property, which is B. This is a vector distributive property. So if I take a dot product of a vector with the sum of two other vectors, then it's the same as if I had dotted U with each of those individual vectors and then just added them afterwards. That's a distributive property. So you can distribute the dot product into the sum of vectors, is basically what that is. That's a simple one to prove as well, which I'm not going to. Also, this one should be obvious, that if I take the sum of two vectors first and then dot it with W, then I get the distribution. So again, it distributes. So these two distribute. But I think that's just true because of a combination of A and B. So letter C is just like a restatement of A and C together. Letter D. This is a different type of distribution, or a different type of distributive property. If you're taking the dot product of a scaled vector with another vector, it's the same as if we had dotted those vectors first and then scaled the result. And that's also the same thing as if I had taken that scaling factor on U and moved it over to V instead, and then dotted it with U. All that's the same. So we can move that stuff around, no problem. Now this looks like an obvious fact, but it's not obvious. First off, that's a boldface 0. That 0 is the vector 0. So that's what we call the 0 vector. And that has components 0, 0. So it's not the number 0, it's the vector 0, which represents no movement. So no change in the x direction, no change in the y direction. So if I take a dot product with any vector, with this vector, do I get the 0 vector back in return? The answer is yes, so we'll see why. 0.u. Well, first off, 0 is 0, 0. And let's say u is a, b. So then if I take the 0 vector, dot it with u being a, b, and we would do it this way. So the definition would be, what's going to be x components multiplied together, which is 0 times a, which ends up being 0, plus 0 times b. That also ends up being 0. The number 0 plus the number 0 is equal to the number 0. So this distinction here, I think they have it written incorrectly. And here's what they should have written. The 0 vector dotted with any vector is equal to the number 0. There's a difference between the 0 vector and the number 0. But yeah, so here they have them both in boldface, so that looks a little confusing. One of them's a vector, the other one's the number 0. So there's a difference between those two zeros. And then the last one, this one's important. That one I want to prove. So if I take a vector and I dot it with itself, you end up getting the magnitude of that vector squared. So let's try it. U dot U. A comma B dot A comma B. A squared plus B squared. Now if you remember, magnitude of U is the square root of A squared times B squared. So this is the square of the square root of A squared plus B squared. And the stuff inside with the square root included, that's the magnitude of U. And the whole thing being squared because there's that extra square on the outside. And so that's proven. So that's a pretty simple one to prove. And those are semi-intuitive properties of the dot product. Somewhat. Okay, so last thing, which is the thing that I'm debating on proving or not proving. And those should be pretty simple. The actual example itself, number 6, A and B, those are pretty simple. That's what I'm referring to. The actual proof of this idea of the geometric interpretation of the dot product, it's kind of lengthy, which I should go ahead and include it anyway. So that's a good idea to see the proof. The geometric interpretation of the dot product. So the angle theta between two vectors u and v, if I plug that into cosine, it's equal to this. U dot v over the magnitude of u times the magnitude of v, which that's not the more intuitive way to write it. The more intuitive way to write it is the dot product between u and v is equal to the product of the magnitudes. So if I'm multiplying two vectors using the dot product, it's the same as if I had just multiplied the length of the vectors times the cosine of the angle. So dot product really is a way to multiply two vectors this way. So you take just the lengths of those vectors and you're going to multiply the lengths of those vectors, but you're also going to scale it by the cosine of the angle. So where does that come from? I'm going to go ahead and try proving it. So proof of, I was going to draw a colon already. So proof of, and I drew a colon again, cosine theta, or no, let's do it this way. U dot V is equal to just the magnitude of U times the magnitude of V times the cosine of theta. So here's a proof of this. So I'll just draw any two vectors. Let's say we have the vector U, and then some other vector V, which I might want to draw those a little bit bigger, or a lot bigger. Move it further down. And the reason being is because I'm going to have to make a parallelogram out of this. Or I don't necessarily have to, but either way. So we want to find out what U dot V is with respect to the angle and the magnitudes. So how do we get that done? The way that we get this done is I draw a triangle for the magnitudes of those, just like we did in the previous section. So we're going to think of this as 8.3, the geometrical treatment. So I'm going to draw a triangle. There's a point here, another point here, and the length of this, or this, the length of that segment in that triangle is going to be the magnitude of V. So that's the distance from here to here. So the side length is the magnitude of V. Side length here is the magnitude of U. So that's the distance from here to here. So the vector itself is the line segment with the arrow. That's the actual linear arrow. But the magnitude would just be the length of the arrow quantity itself. So I'd like to come up with an expression for U dot V. And there's probably a way to do it. Now, from what I remember, in this case, we want the angle theta in between the two. So I want to find out an expression for cosine of that angle. And we have an expression for cosine of that angle. So that's a triangle. We have an included angle, and then we have two sides that include that angle. So this expression includes cosine of an angle. So that's probably why they wrote it that way, because then I could just solve for cosine of theta. Cosine of theta, according to them, was U dot V divided by the product of the magnitudes of U and V. So I would probably just want to come up with an expression for cosine of theta. And we kind of have an expression for cosine of theta. So let's see. We're going to call this C, which I don't know what that is. Or maybe I do. Yeah, I think I do. So this is a little bit of a cheat, and this is something, the reason why I was debating whether or not to show the proof. It's because there's somewhat of a non-intuitive quantity here. Now, if I had done the other diagonal, stemming out from where those two are written together, from theta, let's say, and if we had drawn that diagonal, that's the addition. What's this one, though? This other one. So this one here going this way, this is the addition of U and V. So the one that goes this way is U plus V. What's this one going this way? So that you would need to have understood the geometry between vectors a little bit better to figure that out. This one's U minus V. And here's the way that you do that. You start with U, you draw the negative or the equilibriant of V, which is this way, and then you draw that over here at the terminal of U. And that's going to give you this diagonal, which is precisely the one that we want. So yeah, so that's the cheat. Knowing that ahead of time is something that I already knew, so that's something I already had. That is U minus V. I knew it was going to be V minus U or U minus V, one or the other. So and I don't really care. This is literally just the magnitude of U minus V, or V minus U. Doesn't matter what order you write it in. So there's my triangle. This is the triangle I'm going to work with for this proof. So if you don't really see where that's coming from, that's not something you understood right away, that's not too big of a deal. just know that that's a triangle, and the opposite diagonal is the difference, subtraction of u and v. So one diagonal going from the point where they start from, where they both coincide, that diagonal is the addition. The other opposite diagonal is the subtraction. That's all you got to understand. So knowing all of this that we know, this is just a triangle, and I can apply the law of cosines. So u minus v squared, that's c squared, is equal to a squared plus b squared. In this case, u, magnitude of u squared, magnitude of v squared, minus 2 times a times b, magnitude of u, magnitude of v, times cosine theta. This is the vector version of the law of cosines. And really what we're going to do is we're going to simplify it down to this expression. And that is the final vector form of the law of cosines. So really that's what the dot product is a representation of the law of cosines in vector form. So applying vectors here. Anyway, so what we're going to do is we're going to try to expand this quantity. And that's going to be kind of a tough one. How do I take the square of the magnitude of u minus v? So the way that I'm going to think of it though, the square of the magnitude of any vector is equal to the dot product of that vector with itself. So this is equal to u minus v dot u minus v. Where am I getting that from? I'm getting that from over here, the very, very last one, letter F. So if I have a magnitude of a vector squared, it's the same as if I had just taken the vector inside of the magnitude and dotted it with itself. Same idea here. So if I'm seeing that, just think of u minus v as a single quantity. It has a magnitude of its squared, so take what's inside of the magnitude and dot it with itself. And this is equal to, according to their distributive property, it's going to end up equaling to u dot u, in this case, minus u dot v, because I can write it in whatever order I want, minus another u dot v, and then minus it, that's going to be minus minus, so plus v dot v. So what I did was apply the distributive property from here to here, 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 that one with that one, and this one with this one. So I'm doing the distributive property. Since the distributive properties hold for dot products, scalar addition, we can apply the distributive property of the dot product. So then we simplify. U dot u, which I'm going to say that that's magnitude u squared, and that's because of letter F. These two combine because they're the same vector, minus 2 u dot v. And then this one is the magnitude of v squared according to F again. So this right here is what came out of u minus v magnitude squared. So the magnitude of u minus v quantity squared. So that is going to get set equal to all of this stuff, the stuff on the right hand side. So I'm going to do magnitude u squared minus 2 u dot v plus magnitude v squared, and that's supposed to be equal to magnitude u squared plus magnitude v squared minus 2 magnitude u magnitude v cosine theta, which that's coming from the right hand side of the law of cosines. So now I have this ugly expression here, but a bunch of stuff cancels out. You can subtract magnitude u squared, those go away, subtract magnitude v squared, and what are we left with? Negative 2 u dot v equals negative 2 magnitude u magnitude v cosine theta. And what I'm going to do here is I'm going to divide by negative 2, and that's it. These two negative 2's will cancel, those two negative 2's will cancel, and we get u dot v equals magnitude u magnitude v cosine theta, which is precisely what we set out to prove. Let me zoom out. There's a lot of vertical space there. So I probably could have stretched that out horizontally instead. But that's exactly what we set out to prove. So we've proven it. So that is the polar definition, or the trigonometric definition of the dot product. So we can think of that as just a trigonometric version of the dot product. So it's a way to actually calculate the dot product but using trigonometry instead. So we have a cosine function in there instead. So distances and angles instead. So how is that useful? In this course, the major use that we're going to make out of that is by finding the angle between two vectors. So they're going to give you two vectors. What's the angle between them? In letter A, we have 5, -12, and 4, 3. What's the angle between those two vectors? Well, instead of drawing them and making a triangle and then using law of cosines to find an angle and then law of sines to find the actual angle that we want and stuff like that, we could just use the dot product. So what was the other way? You would draw U, which U's in the second quadrant, V's in the first quadrant. What's the angle between them? You would have to do a triangle. You have this, and you have this, and then you can figure out what this is by adding the two vectors or subtracting the two vectors, and then you would find the angle between them by applying the law of cosines. Too much work. We'll just use a dot product. So, according to this thing, cosine of theta, which is the angle in between, that's exactly what I want, is equal to the dot product of the two divided by the product of the magnitudes of the two. So I got to find out what the dot product is between them, and I have to find out what the magnitude is between them, or for each of them. So the dot product between them, 5 times 4, and then plus -12 times 3. You multiply the x components, you multiply the y components, and then add the results together to get the dot product. Then I have to find the magnitudes for both of those. So the magnitude for the first is the square root of 5 squared plus 12 squared. The negative doesn't matter because you're going to square it anyway. That gets multiplied by the square root of 4 squared plus 3 squared. And I wrote an ugly square here because I accidentally made that a 3. And I have to simplify this quantity. So on the top, 20 minus 36. That's divided by 5 squared plus 12 squared. I know that's a special value. I think it's 13. So that's 25 plus 144 is 169. Square root of 169 is 13. That I knew that ahead of time without doing the math because that's a special right triangle. The 5, 12, 13 special right triangle. Just like a 3, 4, 5, or a, what is it, a 7, 24, 25? There's several others. And this one's a 3, 4, 5, by the way, so I know that this one boils down to 5. You could just try it anyway. 16 plus 9 is 25. Square root of 25 is 5. And we're almost done. This is -16 over 13 times 5 is 65. 16 is only divisible by 4 in itself, 16. 65 is divisible by 13 and 5, and that's it. They have no common factors. They're relatively prime. This is cosine of theta, which I didn't really care if they were reducible. I could just plug this into the calculator at this point. That's not a special angle ratio anyway. So to find out what cosine is, you find out what the angle is. This is inverse cosine of -16 over 65. Now, whatever the calculator is going to give me, I have to be careful with it. So I need to find out how big the angle is supposed to be. Actually, no, I don't really care, do I? It's just the angle between two vectors. One of them is going to be smaller than 180, and the other one's going to be bigger than 180. We'll just take the one that's smaller than 180 degrees, and that's going to be precisely the one that the calculator is going to spit out for me. And the weird case is where it's 180 exactly between the two. So we're doing the inverse cosine of -16 over 65. And that looks like a 15 the way I wrote it, but it's supposed to be a 16. And I'm getting 104.25 degrees. They didn't tell me what to round to, so I'll just leave it as 0.25. So 104.25 is the angle that I have here. The letter B is done almost exactly the same way. So my guess for the next one, because I'm already looking at it, 3 and 4. This is also a 3 and a 4. That's just 2 times 3, 4. So if I take the dot product, u dot v, between those two, it's going to be 4 times 6 plus negative 3 times 8. 4 times 6 is 24. Negative 3 times 8 is negative 24. And we get 0. The dot product of two vectors ends up equaling to 0. It's because the angle between them is 90 degrees. And that's because I saw ahead of time that 6 and 8 is a multiple of 4, 3, or 3, 4. So right away, my idea was just to take the dot product of the two. But what you could do is you could still apply the formula. If you take the dot product between the two, cosine theta is equal to the dot product of u and v divided by two scalar quantities being multiplied by each other, something and something else. The top is 0. That tells me that cosine theta is equal to 0. So I don't even have to care about what the bottom is, as long as the bottom's not 0, and it's not. So if cosine is equal to 0, automatically you should know that cosine, or theta for that particular situation is equal to 90 degrees, because cosine of 90 is 0. Sounds an easy one. And that's going to be it for this particular section.